Hi there, and welcome to Unit 2, Dynamics and Uniform Circular Motion, and our first video lesson. So in Unit 1, we focused a lot on setting up a lot of our background and constructs of how we quantify and describe motion. And we led us to all the kinematic equations and a few different interesting applications such as projectile motion to quantify. Now in Unit 2, we're going to dive into a different way of analyzing motion. And when I say the concept of dynamics, that means we're taking a look at forces. And what forces cause, as we'll talk about later, is acceleration. So we're taking a look at one piece of what we talked about already, the acceleration piece, and trying to understand where exactly that comes from. Additionally, at the end, we will be covering this concept or talking about this concept of uniform circular motion. And with uniform circular motion, that's just that. It's an object that goes in a circle with a constant speed, and we'll talk about some of the implications of that. Now, a little bit of quick background on dynamics. Dynamics is specifically the branch of mechanics concerned with the motion of bodies under the action of forces. Now, mechanics literally just means it's the quantification of motion. So last time, kinematics was by taking a look using kinematic equations and understanding acceleration and velocity and those things. So we use those to quantitatively describe an object's motion. Dynamics is using the forces acting on them to solve for the acceleration component of that motion, and then we can take that back to kinematics to make additional observations. So really, this is an extension, or you could say that the more intricate or next step in what we've already talked about. So we're going to start by taking a look at the biggest name in physics, but the biggest name associated when we talk about forces, and we're going to start by looking at Newton's laws. Now, Newton has three laws that govern dynamics, and we're going to take a look at each of those throughout the course of this unit. In this first pre-lecture video, Brian Jones starts with a simple demonstration of applying a force to an object. And in that force, he's using this hacksaw blade that you can see in this actually right there. And he's letting it bend to a certain amount to try to measure that force. And this pickup truck over here, it undergoes some motion. And he makes a free body diagram, and we see that indeed we have a force being applied that causes acceleration. And more specifically, it causes a constant acceleration, which we've already talked about as being non-uniform motion. So the first big demonstration is just that. It's solving for a piece of the puzzle that we've already talked about by looking at what causes acceleration. Then he adds mass, more mass to the truck. Now, in last unit, we talked nothing about mass, absolutely nothing about mass. But now, in this unit, we're going to have to take that into consideration when we take a look at the forces that are being applied to an object. And then after the truck experiment, he gets into a little bit more about talking about how forces are an interaction between two objects. And then he goes on by demonstrating a couple of things with these spring toys. So we'll talk a lot about Newton's third law, which all forces occur as part of an action-reaction pair, and how if I push on to something, it's pushing back on me. But he kind of preludes that in this first little pre-lecture video. Okay, so the very first section of this chapter is taking a look at motion and forces. So how is motion related, or what causes motion, and how it relates to forces? And that's the first thing we'll take a look at. Okay, so we can ask ourselves the question, what actually causes motion? In the last unit, we just said, hey, motion's happening. Well, let's take a look at this quick little example. In example A, we have a student, or a student doesn't have to be a student. We have a kid on a sled, and that kid on a sled, if he's on a sled on some smooth snow, the sled will come to rest. And we've seen, you probably have gone sledding, and you go down to the bottom of the hill, and your sled comes to rest on its own. But if we think about changing this concept, and instead we're going to go on some slick ice. So maybe you're sledding by the lake, and then your sled goes onto the ice, and it might go quite a much larger distance. So on that slick ice, the sled slides further. Now, if I think about in physics, we always talk about like a frictionless surface, and a frictionless surface means just that there is no friction. And if friction could be reduced to zero, the sled would just keep going and going and going and never stop. So in the absence of friction, if the sled is in motion or if the sled is moving, it will stay in motion. And that'll actually bring us to Newton's first law. Newton's first law is that an object, if it has no forces acting on it, then if it's at rest, it'll stay at rest. If it's in motion, it'll continue to stay in motion at a constant speed. So Newton's first law we often refer to as the law of inertia. An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless an outside force acts upon it. That's the simplest definition of Newton's first law. And it means that if there are no forces acting on something, then something will stay in motion or it'll stay at rest at a constant speed. A little historical significance, Aristotle was actually the one who initially said a force is required to keep an object in motion. And if I think about that, that actually kind of makes sense too, because if I'm pushing a fridge, for example, I need to use a very big constant force just to have constant velocity. But in reality, that's not the case. I'm actually overcoming friction the entire time. So Newton was the one who said, no, that's not quite right. And then he came up with some laws of motion to help explain and describe what is actually going on. So we have to ask ourselves then, if we're talking about Newton's first law and we're talking about forces, what is a force? No, I am not a force. I am your teacher. So please stop calling me that. But anyway, a force is a push or a pull on an object. It's a very simple definition. It's a push or a pull on an object. Every force has its own agent or something that acts or pushes or pulls on it. So in this, we got this track athlete over here. She's got the shot put, and she has to push the shot put in order to get it to move. Now, that shot put, of course, will in fact follow a projectile motion, as we have previously discussed, but something has to get that initial velocity. So the agent is the person that's doing the force. So here we have a football player. He's the agent on the football. And then we have an object, and that's something that's receiving the force. So we'll categorize those two things as we talk about forces. Now, forces are a vector quantity. So it means that it has both magnitude and direction. For forces, we use a capital letter F, and the magnitude is just the letter F, but as you'll see, I try to be consistent, and I use this little vector symbol at the top of it, because that would be the correct way of making sure that we know it's a vector. And we'll take a look at a couple different types of forces, but really they fall into two different categories. We have contact forces, which literally means that, yeah, the force needs to be contacted, or it's something that's physically pushed or pulled through touching at a point of contact. But we'll also take a look at long-range forces. And forces that are long-range forces, they're forces that they act without physical contact. And there's a few different categories of those that we'll talk about. For example, gravity, right? Gravity is always acting, even if I'm hundreds of feet into the air. It's a range force. We think about magnets. Magnets attract each other or repel each other, and we feel that from a distance apart. And we'll also take a look at electric charges, and we'll actually come back to that later in the year in our last unit. All right, so when we take a look at a force vector, we got to think about the easiest concept is thinking about how we're applying that force. So in this first picture up in this corner, we have this nice little representation. Here's a box, and this person is pulling on the box. Well, if the box is the object, we represent it with a single point, and then we draw the force acting in some direction. And we'll come back to this concept. This concept is known as when we draw a free body diagram. But we represent the object as a particle, and we just draw as a force leaving that particle the direction of motion. Now, or the direction that the force is applied. Now, this can be confusing because this person is pulling. So some people might say, well, isn't the force kind of on this rope? And that's not correct. The direction that we look at is just based on the direction of the object, and that object is being pulled to the right. In the second concept, we're taking a look at a box being in the air. So then gravity is going to pull it straight down, and Earth is acting as the agent, causing that range force of gravity. We also will label each of our forces. So here, this is T for tension, and we'll build a catalog of forces very soon. And then here's W for weight, aka the force of gravity. Now, I can also have multiple forces acting on one object, and this will get us into Newton's second law, which we'll talk about a little later. But for example, if I had, we'll call it a teddy bear instead of a box because it makes more sense. If I have two people pulling on a teddy bear, one person pulling straight down, one person pulling up and to the right, there can't be two directions of motion unless you rip the teddy bear. So when we simplify this with the force diagram or the force vectors, we have the particle for the box. One person is pulling down, one person is pulling up and to the right, and then I get this net force, which is a combination of those two forces, which is in this case down and to the right. And we can get into some really tricky problems that deal with forces acting at angles. We got to break everything down into components, and things can get very, very confusing. Now, we'll take a look at some of those problems, but we'll actually keep it relatively simple as we go through this unit because we're getting the overview and we're moving on. So I got a quick check for you in the notes, and we're taking a look at two forces acting, and if we had a third force to cancel it out, so here are our two forces that are acting in this corner over here. If I have two forces acting, what force would cancel it out? And in this case, I have a positive y component and a positive x component, which means to cancel it out, I need a negative x component and a negative y component. So the answer is this force right here, because that force is pulling down and to the left, which gives me my negative x and negative y component. And that, at this point, is all we're going to really introduce with taking a look at forces. Now, where we go from here is now we got a quick little introduction to forces. So now we want to build a catalog of forces and think about what types of forces can be acting on as an object. As always, we have to start with the explanation of things before we can really get into the quantification. So we'll start by taking a look at an easy way of approaching that, and then later we will add the quantification piece. And we'll start that in the next segment by building a catalog of forces.